So what if I decide I want to center my polynomial at x equals some value c, c for center. So we've already looked at examples where we build our approximation at x equals 0, at x equals 1. Now it's totally in general. Is there a really fast way to calculate the numbers here that would go in our polynomial representation, where we've got a constant plus a coefficient on x minus c, plus a coefficient on x minus c squared, x minus c cubed, and so on? The answer is yes and no. Let's go through that same process for the last time. So the process, you remember, was we've got some function f of x, and we've got our polynomial. And so we want to set f, before we set f of 0 equal to p of 0, but now since we're centering at a value c, we want f of c to be equal to p of c, f prime of c to be equal to p prime of c, and so on. We want to set all the derivatives equal. Well, okay, so our function f we'll just call f. So let's write out the first couple of derivatives for f. And if I'm evaluating them at x equals c, that's just saying f of c, f prime of c, f double prime of c, and so on. Okay, so what are we setting those equal to? All the derivatives of our polynomial. Well, notice that every single time we've done this process, the derivatives on this side have always come out to be the same. We always get factorials times the coefficients. So I would encourage you to try it again yourself, because it's very instructive if you don't understand the pattern yet. It still feels like you're doing stuff and not really seeing it. Really pay attention to how the pattern ends up getting you these same values every time. But we will, in fact, get these same values every time. All right, so if we're going to generalize now, the nth equation down, we're going to have the nth derivative evaluated as center c, and we'll have n factorial times a to the n. So we want to solve for that a to the n, so that gives us a completely general equation for the nth coefficient. We have the nth derivative evaluated at the center divided by n factorial. So where does that get us with our original approximation? We know that the polynomial will look like this. We've got a bunch of different powers of x minus c, and we want to solve for these coefficients. And now we have an equation for the general coefficient. So this is the coefficient when n equals 0, that's the coefficient when n equals 1, and so on. So I can sort of just substitute and think about it. So let's see, the 0th derivative is the same thing as the function itself, evaluated at c, and 0 factorial is equal to 1. Here I've got f prime of c divided by 1. Here I've got f double prime of c over 2 factorial. Here I've got f triple prime of c divided by 3 factorial. And then when you need specific numbers here, of course, you actually still have to find what is the third derivative of your original function and then evaluate it at c. But at least sort of now this is a general way of writing down the same pattern that's been happening every time.